Welcome. This course is an introduction to extremal combinatorics. So the purpose of this course is to cover all the basics of the different contents, different topics in extremal combinatorics. It's a big field with a good variety of problems and directions. So we will start with contents grouped by the topic. That's the first part. And the plan is in the second part, then after we cover the basics, we move on to focus on more different methods. And that will be part 2. So the first announcement is that there's a WeChat group here. As you can see, this QR code. So if you want to join, you can scan this code. So the first week, we will start with recalling all these basic discrete structures that we will be studying. We will start out very slowly. We only assume very basic knowledge about graphs, but even that, whenever we talk about problem, I try to give the definition and try to recall the necessary definitions. So if you have any questions, you can type in the chat or on Zoom, and I will try to pay attention to that. So the extremal combinatorics is basically studying the extremal type of problems for discrete objects. And the most studied objects throughout this course will be graphs. So let's first recall. So this graph, a very basic concept. So the graph consists of vertices. So here V is a set of vertices and edges. Okay. Edges are binary symmetric relations between vertices. So here's an example. We have a 5-vertex. Here's a 5-vertex graph. We have 5 vertices and 5 edges. Okay. So between 2 vertices, we only have 2 types of relation. Either there's an edge or there's no edge. That's it. It's very simple. Discrete objects. What can we do with this object? Well, very roughly speaking, nowadays we use a lot of internet, and all these networks can be modeled by graphs, right? We can imagine each one of these nodes as one of the users, say WeChat user. And if 2 WeChat users, they are friends, then you can indicate this relation by adding an edge between them. If they are not a friend, then there's no edge. So this is just a very simple example. Let's start by recalling some basic graph families that will be studied, that will be useful. So perhaps the most basic family is path. Okay, this graph, as the name indicates, just look like a path. You have vertices line up in a linear order, and you only have an edge between consecutive 2 vertices on this order. Okay. And the next, perhaps most basic one, is a cycle. You can see in this path, the 2 ends, we didn't close it up. So if you add an edge between 2 ends, we will obtain a cycle. In other words, you can arrange the vertices in a cyclic way, and 2 vertices adjacent if only if on this cyclic order they are adjacent. Okay. Very basic families. The next basic family, rather dense, is the complete graph. Or let me write the notation. So for path, we will use standard notation. P stands for path, and the sub-index will be the number of vertices is always the order, the number of vertices in this path. And sometimes the number of vertices, we also call it the order of the path. Okay. In this example, we do, how do we 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a P9. This is the P9. This is a cycle. We will use C with 8 vertices. So this is C8. So for complete graph, we will use K on T vertices. That just means, let's draw T equal to 4. We have 4 vertices, and between every pair, we're going to add an edge. Very simple graph family. The densest possible graph. Generalizing complete graph, we can have complete multipartite graph. Let me write K, M1, M2, MR. Let's say we have R parts. So what is this graph? You have R parts. The first part has M1 vertices, second part has M2 vertices, and the last part you have MR vertices, right? You have R parts. And each part is independent, there's no edge inside in each part. And you have all edges between different parts. So here, that means we have all edges between all these different parts. Okay. Now we can already, let me mention one more basic things, and then we can start warming up with some very baby version of the extremal problems in graph theory, which I believe most of you learned it, but let's start with these examples to get a feeling of how problems look like in extremal graph theory. So one more notation is the degree of a vertex. Let's say V. I usually will write D of V. Okay, this is just the number of edges incident to a vertex. So in this example, we have these 2 vertices, right? And this vertex will have degree equal to 3. You have 3 edges incident to it. And this vertex will have degree 2. You have these 2 edges incident to you. Very simple. So if you haven't seen this before, some of you are early undergraduate students, you haven't seen graph notion before, you can try to prove this proposition. It's a simple exercise. Is that for any graph G, the number of edges I will use this notion, E of G, times 2 equals to the sum of degree of all vertices. Okay. So you sum over the degree of every vertex in V, you will end up with 2 times the number of edges. So, okay. One more notation is we'll use, for graph G, we'll write delta G. This is quite standard as the minimum degree of G, meaning you look at the degree of every vertex and you take the minimum over the vertex sets. Delta G is the maximum. Okay. Good. Let's start by these simple exercises to have some idea of the extremal problem. So perhaps one of the results we learn, before this, maybe let me mention subgraph containment, the definition. So we have 2 graphs H and F given, two graphs, H and G. We say H is a subgraph of G, denoted by H is a subgraph of G if you can find the injective map, let's say phi, from the vertex set of H to vertex set of G, preserving adjacency. Namely, whenever you have two vertices, that's an edge in H, under this map, they must also be an edge, but in the target graph, which is G, okay? Here's a very simple example. Suppose we have, say, this full cycle is H. And this is our G, right? Then we can do this map. Blue maps to blue, red maps to red. There are many different ways. Just pick one way. Green, let's say it can goes here. And we have purple, it goes here, right? It's easy to check that this is an injective map preserving the adjacencies. In other words, you can find a copy of this graph inside G. If there's no such map, we will say G is H-free. We say G is H-free. Okay. So let's start with the first simple result about subgraph containment. We've introduced these path, cycles, and complete graphs. So most of the problems in extremal graph theory looks like the following. We find some sufficient condition that guarantee the existence or appearance of subgraph inside the host graph. Here's a very, very simple example. For every graph, G, every graph G with average degree, I will denote it by D of G. What's the average degree? Just the sum of the degree of all vertices divided by the total number of vertices, okay? If the average degree is at least 2, then we know the graph contains a cycle. Here is the cycle, which is a subgraph of G. I will leave this as exercise if I haven't seen it before. So this is exercise. Now, after seeing these results, so throughout this course, not only we will give some basics, and we also try to develop a way of thinking, preparing for research in extremal graph theory, extremal combinatorics. So after seeing these results, what kind of question we can ask? So we have a sufficient condition guaranteeing the appearance of the substructure. In this case, we cared about cycle, so cycle appears. Then the next natural question is, how tight is this bound, right? Can we put 1.9? So exercise is to prove this. And the second exercise, remark. And second exercise, simple exercise, is this bound tight or optimal? Can it be 1.99? Okay, I can tell you the answer is no. So think of an example. illustrating that it cannot be anything smaller than 2. Okay, that's a very good question one can ask. Basically, whenever you see an extremal combinatorics result, if it involves some quantity, the first thought that comes into our mind is this bound optimal? Okay. Now, after we ask question about hypothesis, can also ask question about conclusion. We know the appearance of a cycle, but what can we say about the cycle? Can we, ideally, larger substructures are nicer, right? Can we have a longer cycle? And the answer is also no. We have no control. So here's a remark. We cannot say anything about this cycle. So no control. What do I mean by this? Let's consider this example. We have, say, n vertices, 1, 2, 3, labeled. You have n vertices, right? Let's consider average degree 2 is the same as, if average degree 2, as I said, you have n vertices, that means degree sum is 2n, and degree sum is 2 times the number of edges. So the number of edges in G is n. The number of edges is the same as the number of vertices. What do I mean by, if all we know is the average degree is at least 2, we have zero control over how long the cycle can be, because the graph can simply look like you have a path, go all the way from 1 to n. How many edges? Blue edges. You have n minus 1 blue edges. And then you could have an edge that could be as short as 1, 3. Then it has n edges. We satisfy the hypothesis, average degree 2. And the cycle is shortest possible, 3. And this edge could also be here, right? Can be anywhere. It could be from 1 to I. It could be from any pair of vertices. So the cycle could be of any length. We cannot control. A natural question one can ask, and a lot of people care, is what kind of sufficient condition will guarantee a longer cycle, right? How can we modify this proposition to obtain a stronger conclusion? Stronger conclusion requires stronger hypothesis. Okay, we will see immediately a strengthening of this proposition. But this is just a baby illustration. Whenever in the future you see the example, I hope that you can practice this way of thinking. Is the bound optimal? Can we strengthen the substructure obtained? Etc. Think of the questions and possible future directions. So here's a strengthening proposition. Now, instead of working with average degree, let's work with minimum degree. Not necessarily, but things are much easier. This is the first week. We will ease into the material. So let's start with some basic things. For any graph G, if we know the average degree is at least D, say, now we can, for some natural number D, let's say natural number at least 2, we've seen the D with the 2 case. So if minimum degree is at least 2, then there exists a cycle of length of number of vertices at least D plus 1. Maybe I shouldn't write like this. There exists a cycle of length at least D plus 1 in G. Now we've obtained what we wanted to do, right? Before we have no control on cycle. Now if we increase the minimum degree from 2 to larger number D, we can guarantee a cycle of longer length. So let's see this proof first. It's also very, very simple proof. So the proof is, let's take the longest path. Let's say starting point, starting at some vertex V. So here's our path. da, 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 da. This is the longest. Okay, here's the end vertex. Longest path means what? The longest means that the neighbor of V, so this is the set of all neighbors. That means the set of all vertices adjacent to V, all neighbors of V. They must all, let me use blue. They must all lie on this path, right? Why? Suppose otherwise. If you have a neighbor V that goes out of this path, then we could have extended this path to a longer one with length 1 more. That's a contradiction to our choice of this path. Okay? And now the result follow immediately because what do we know? We know the minimum degree is d plus 1. So you have one neighbor here, right? So this is the first neighbor, second neighbor, third, dot, 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 to this neighbor. You have at least d neighbors, all of which lie on this path, including the vertex itself. So this already, if you go all the way here, coming back, this will give you the cycle. Maybe I can use highlight, yes. So you can go all the way, too thick. You can go all the way, and you go back. You get this cycle. Desired cycle. Okay, very simple. What can we do after this? Anyone? Is this bound tight, right? That's the first question we were trying to practice before. Remember here, is this 2 optimal? We can ask the same thing here. If you have minimum degree D, what does it mean? Is it optimal? Then can we guarantee D plus 2 length cycle? The answer is no. So this is also tight. Remark, this bound is again optimal. You can consider G to be complete graph on D plus 1 vertices. Okay. Every vertex has degree D in this graph. And the longest cycle is no more than the total number of vertices in this complete graph, which is D plus 1. So we cannot hope to do better. In the later part of the course, we can see nonetheless, even though this is optimal, we can still generalize in other directions. But that's later story. Any questions so far?
We always assume that graph is a finite graph.
We always assume, yeah, throughout this course, most of the time we consider finite graphs. That's true. Okay, good. I like questions. All right, so let me give you an exercise, one more exercise to finish these very basic parts. So, and using this exercise, I also introduce a new family of graphs. So this is a family of trees, a family of graphs. So what is a tree? So a graph, a tree is a graph without any cycle as a subgraph. It's also a very important and basic concept. So sometimes people say acyclic. Acyclic means without. So acyclic means without any cycle as a subgraph. Okay. An example, the path we see is a very special tree, right? And this kind of graph is also a tree. People call it star. You have a central vertex and all the edges incident to this vertex. And there are more complicated trees. This is a very common one, a binary tree. Binary means every vertex branch out to 2. You go down, branch out to 2, and you can keep going. There's no cycle, very easy to check. So here's the exercise for you to try to get more familiar. Try to prove exercise that so we've seen sufficient conditions guaranteeing existence of cycle. So let's try to do something like sufficient conditions guaranteeing existence of a tree. Okay. So here's the exercise. For any tree on T vertices, sometimes if you haven't done this exercise before, always good to visualize the problem. So you can try to take a tree on small number of vertices and try to solve these small cases. And then you try to generalize your arguments, right? Let's say on T vertices, T is a natural number. Let's call it T. So let's imagine, here's an example for you to visualize. Let's say T equal to 5. And you have 1, 2, 3, 4, 5. And this is the tree, for example, right? For any tree on T vertices, then we have the following sufficient condition that can guarantee the existence of T as a subgraph, this tree. For any graph G, if the minimum degree is at least T minus 1, then we know we can find such tree as a subgraph of our graph G. Okay. Optimality is also trivial. Again, we can ask the same thing. This bound is optimal because G can be simply KT. KT has minimum degree T minus 1 once again, so we cannot have anything more than T vertices as a subgraph. Okay. So this is the basic family of graphs and some very, very baby version of the extremal problems. Any questions so far? So if not, let's move on to perhaps one of the very first theorem in extremal graph theory, is Mantel's theorem. Okay. So for Mantel's theorem, what does he say? He says the following. Let me state the theorem. He says, for any graph G satisfying 2 conditions, the first condition is it's triangle free or K3 free. Sometimes I'm lazy to write K3, complete graph on 3 vertices. Just you have these 3 vertices pairwise adjacent, right? You don't have 3 vertices in your graph that are pairwise adjacent. That's the condition. And let's say you have m vertices, m vertex. The question is, how many edges you can have? Okay, what's the maximum number of edges? And Mantel says that E of G is at most n squared over 4. So let's try to be precise. I take a floor of this number. So remember the exercise we're trying to do, the mental exercise, is this bound optimal? Let's try to think. What does it mean, is this bound optimal? Well, I can tell you the bound is, it is optimal. This is optimal. What does it mean optimal? That means we cannot hope to obtain the upper bound that's any better than n squared over 4. If you put n squared over 4 minus 1, it becomes false, this conclusion. And the example is not hard to If you haven't seen it before, you can come up with example showing the tightness fairly easily. Let me just tell you the this example. So the tightness example is, what we can do is we can simply partition the vertex set of n vertices into two almost equal parts. Right? You have n over 2 vertices here. You have n over 2 vertices here, floor and ceiling. And you add all the edges between them. Okay. This graph obviously does not have triangle. If you have a triangle, you will have 3 vertices by pigeonhole, 2 of which lying on the same side. Let's say on the left-hand side, right? But we didn't put any edges inside left side or right side. So this you cannot have triangle. Very good. And the number of edges is precisely, you multiply these two, this number n squared over 4. So this is optimal. Good. So let's give a proof of this. We will actually give 2 proofs, combinatorial proofs, and review some basic discrete mathematics we learned in undergraduate. First or second year undergraduate, we learn discrete mathematics. We learn how to do induction, right? Let's do an induction proof. Okay. Is the goal clear? We have triangle-free graphs on n vertices. We want to prove that it cannot have more than n squared over 4 edges. So the first proof, by induction proof. This is actually the this induction proof. So induction on the number of vertices n. Base case, I will leave it as exercise for you to check. You just check n equal to 1, 2, 3, 4, 5. No triangle, very easy to try all possible subgraph, verifying the bound. So base case is easy, trivial. Let's look at the inductive step. Okay. So what we're going to do is we're going to grab an edge. If the graph has no edge, we will take a graph G, triangle free on n vertices. If there's no edge, nothing to prove. E of G is 0. So assume there's an edge. Let's take an edge. Let's call it X and Y. Okay. Good. Now let's consider how the rest of the vertices sending edges to X and Y. Okay, so here is the rest of the vertices. This is B of G minus X and Y. Let's take a vertex, let's say Z, and see how. Can Z send edges to both X and Y? We cannot, right? So either you're adjacent to X. If you're adjacent to X, you cannot be adjacent to Y, otherwise there's a triangle. So that means for every vertex in every vertex Z not equal to X and Y is adjacent to at most one edge, a vertex in XY by triangle freeness. Okay, good. And we are done. Why? Let's count the total number of edges. So E of G is at most 1. This is the XY edge. Okay. Plus, we have n minus 2 vertices in the rest. You have n vertices in total. Each vertex can send at most one edge to XY. So the cross edges is n minus 2. Plus n minus 2. This is edges from V minus XY to xy, right? Plus the last term. But what are the remaining edges? We have count this edge, 1. We have all count the blue crossing edges. Maybe I can use blue so it will be more clear. And all the remaining edges lie in this box, right? And this is a strictly smaller graph. We can invoke our induction hypothesis. So inside here, by induction hypothesis, IH, induction hypothesis, the number of edges is m minus 2 over square over 4 floor. Okay, and if you solve this, you get n squared over 4. Take a floor. I will skip doing this calculation. This is simple calculation. And this finishes the proof. Any question? Very simple proof. Okay. Basically, the observation is we have to make use of triangle freeness. And how we make use of it is if you grab an edge, every vertex can send at most one edge to endpoints of this edge. So that's the first proof. Let's look at a different proof. The first proof is quite combinatorial. The second proof is also quite combinatorial. Another combinatorial proof. This proof is by taking a max degree vertex without using induction. So without using induction, how can we prove it? Let's consider a vertex of maximum degree. So let's say dv is our maximum degree vertex. No vertex has larger degree than v. Now, let's say dx. This is our x vertex, and this is its neighborhood. Let's call it capital X. Is the neighborhood of v. Okay. Well, first of all, observation is the graph is triangle free. That means the neighborhood of v, namely the set x, there's no edges inside, right? Implies no edge in x. Okay. Now let's let y to be the rest of the vertices, v minus capital X. So little x is in y. Good. What does this piece of information telling us? No edge inside x. We have a partition of the vertex of v, right? We have x, the neighborhood of v, and y, the rest. If there's no edge inside x, that means every edge in this graph, either between x, y, or inside y. In other words, every edge in G is incident to at least one vertex in y, right? At least one vertex. If it's one, it looks like this. If incident to two vertices in y, it looks like this. So, no edge in y implies every edge in G is incident to a vertex in y, at least one vertex in y. And what that means is that we can give an upper bound on the number of edges by the sum of dy y in y. Okay, this is overcounting, because if the degree, this y, right? If the degree, the edge is going across, it's counted exactly once in the number of edges. If it sends inside, let's say y prime, then this edge, this degree, is counted by y from y side and also from y prime side. So these kind of inner edges in y actually counted twice, but that's not a problem. It's an upper bound. So far, so good. What next? Remember our choice of x. Our choice of x is a vertex of maximum degree. Meaning what? All the other vertices, their degree is at most that of x. So we can upper bound this quantity, this by choice of x. We know that it's at most sum of dx, right? What? Let me just write dx. But what is dx? Dx is just size of x. And how many vertices we are summing up? Number of size of y. So this is at most x times y. Okay. Now we just use basic inequality. X times y is at most x plus y over 2. The geometric mean is at most the arithmetic mean. And that's precisely x plus y is everything. So it's n squared over 4. We prove that E of g is at most n squared over 4. It must be an integer, so it's the floor of n squared over 4. It's another proof. Also very simple proof. Okay, both proofs just by some ad hoc combinatorial arguments. Any questions so far? If there's no question, I have questions for you. So this is actually not everything of Mantel's theorem. Remember, so what we did is we proved that every triangle free graph on n vertices must have at most this number of edges. And we've also saw an example realizing this maximum, n squared over 4. What would be a natural question to ask? Are there other maximizer? Is this maximizer unique, right? Can we characterize, if it's not unique, can you say how the other maximizer look like? Can you characterize this, the set of all maximizers? This is a very natural question. In this case, actually, in Mantel's theorem, it's not hard to see from these two proofs, from first proof and second proof, you can work a little bit harder to prove that this is the only graph on n vertices realizing the maximum bound. I will leave that as exercise for you. So the first exercise, first exercise for Mantel theorem, prove that this complete bipartite graph with n over 2 vertices on one part and the floor ceiling of n over 2 vertices on the other part. This is a complete bipartite graph, remember? It looks like this. Is the unique maximizer. Sometimes people also call it extremal graph for this problem, for triangle containment problem. Okay. Good. All right. If there's no question, we gonna move on to a slightly different. So we've seen graphs. We've also seen this first results in extremal graph theory, extremal flavor, Mantel's theorem. Now let's review different discrete structures that we'll be studying a lot throughout this course. Find sets, a collection of finite sets on the It's mostly bounded number of elements. So this is, let's look at results about sets. Okay. Oh, before this result about set, I have another exercise here. Okay, I'll give this exercise afterwards. There will be homework. So we will share the homework later. I will not mention it here. So let's move on to sets. Let's consider this practical question. This baby example we are looking is called odd town, even town problem. We studied this as a warm-up problem because we will see some extreme problems about sets rather than graphs. And also we will see somehow at the first glance, it has nothing to do with linear algebra, but we can somehow use linear algebraic methods to prove some combinatorial statements. Okay. So what is this odd town, even town problem? The setup is very simple. So here's the setup. We have a town. We have a city or a town of n people, n residents. Let's call these people just 1, 2, label them n. So each person is labeled by a number from 1 to n. For shorthand notation in the future, I will write bracket n to indicate this set, the set of first n integers. Okay. So we have a town of n people, and they want to form up some clubs, different clubs, according to different hobbies. Some people, they like to play football. Some people, they like to play basketball. Some people, they want to listen to music. Some people like movies. So they form into these movie clubs, football clubs, different clubs. The requirement is, so they want to form into clubs, form into different clubs. Let's call clubs C1, C2, ... different clubs. Each club, if you view it as a set, each CI, the club CI, is a subset of the set of all people, right? Some subset of the people, they form into a club. Okay. The requirement is that if you take any two different clubs, their intersection, the common members they have must be an even number. So we need, for any distinct clubs, CI, CJ, the number of people going to both of the club must be an even number. It's an even number, okay? Now, let's do a simpler question. First question. On top of this rule that different clubs must have even intersection size, if we also require each club must admit even number of members. So if each club CI admits even number of people, then what's the maximum number of clubs there can be? How many clubs you can form? Different clubs. If you have m people, each club Ci has size even. Different Ci, Cj, their intersection is even. How many clubs? We want to build many clubs. Okay, we have many choices for different people to join the club, but they have to follow these two rules. Each club even size, different clubs intersection even size. The answer, well, a moment of thought shows that we can actually build many clubs satisfying these two rules. Here's an example. Here's an answer. We can have exponentially many. Exponential in n, many. Why? What we can do is we can group up the residents in this town by pairs. You group them up by pairs. Group people into pairs. Let's say 1, 2 is a pair. The person number 4 and person number 3 is a pair. And then person n-1 and person n is a pair. That's for simplicity, n is an even number. Okay, so I don't need to consider. So we group them into pairs. Now what we can do is how many pairs we have. The number of pairs is n over 2, right? Now, if you think of this pair as an element, you take all possible subset of pairs, and they are different clubs. You can let clubs to be all possible combination, so pairs. How many such ways? You have 2 to the n over 2 ways, right? You could have an empty club with no pair in it, or you have a club with 1 pair, you have a club with 2 pair, you have a club with 3 pair, so on and so forth. You have 2 to the n over 2 choices. And let's check the 2 conditions. Well, first of all, everything comes in pair, so the size of every club is even. And all their intersection is also some pairs, union of pairs. So the intersection is also even. In other words, if we require even intersection and each club even, we can have many exponential in n. Now let's twist the problem a little bit. What if we still require different clubs? They have even intersection, but we ask that every club has odd size instead of even size. Question 2. What if each club has odd size? Okay, let's first try to give a construction. At least we have some clubs. What will be a choice of clubs that, namely family of subset of n, such that each club is odd size, intersection is even size? Can you give me an example that has many, hopefully you have many clubs. If each club must have odd size, the easiest thing you can do is just admit 1 people. 1 is odd number. So let's try Ci, the ith club, just the singleton I. Okay, then obviously this is odd. And for different Ci, Cj is 0, which is even. So trivially it satisfies the condition. How many clubs there are? The number of clubs is n. Okay. But naturally, before, under the even condition, we have 2 to the n over 2. Now we only have n. So perhaps we can do better. That's a very natural thing we are thinking about. We just change the rule a little bit. How can we drop so much from exponential in n to linear in n? This is a huge different order of magnitude. But surprisingly, in fact, n is the best we can do under these changed rules. And we're going to give a proof of this using linear algebra. So this is the theorem. Let me state it completely in math terms. So for any family F, which is a family of a power set of n, so this notation is just all subset of power sets of n, meaning the family of all subsets of the first n integer. Okay. You have some collection of subset of n, that's F. If we know first condition, for each set F in F, you should think of this as a club. It has odd size. Each distinct pair in F, their intersection, the common members is even. That's the new setup, right? We're going to prove that there cannot be too many clubs. What does it mean? We need to prove that the number of sets in this family are indicated by F. This is the number of sets in F is at most n. Okay, so how do we prove that? A very beautiful proof. We're going to think of things in a linear algebraic way. So for every set, we consider its characteristic vector. What does it mean? So we consider its characteristic vector for each F in F. This just means very simple. Let's say here's example, n equal to 5. So you have 1, 2, 3, 4, 5. This is your whole set, n, right? So if you have a subset F that looks like 2, 4, 5, then 1F is just a length 5 a vector. Right? If element 5 is in F, the fifth coordinate is 1. Element 4 is in F, so the fourth coordinate is 1. Element 3 is not in F, so this third coordinate is 0, so on and so forth. So you use a length n binary vector indicating which element is in your set. This is a natural one-to-one correspondence characteristic vector for F. Good. Now let's translate all the conditions we have into linear algebraic terms. What does it mean that every club F has odd size? Well, the first condition, let's write 1 and 2, right? The first condition implies what? If you take the inner product of two characteristic vectors coming from the same sets, you will get an odd number, right? And odd number, let's do everything modular F2, modular 2. So this equal to 1 in F2 or Z2. Good. What about second condition? Second condition says if you take the intersection of two different sets, but what is this intersection? This is precisely the inner product of their characteristic vector, right? It's just 1F, 1F prime. It's again their inner product. And this is even number. That means it's 0 in F2. If it helps, you can think of it as a matrix, right? You have F, F prime, F, F prime, dot, dot, dot. This is elements. This is the matrix, elements in your F. If you take their inner product, you only have diagonal one. Maybe this is not very helpful. Forget about this. So anyway, we have for every element, for every set in F, we have a vector. And this vector form an orthonormal basis of F2 to the n. That's what it says. So that means maybe not orthonormal basis, just that they are linearly independent, right? They are linearly independent. Because we don't know if they, yes, they are pairwise orthogonal. Pairwise orthogonal. You take the same thing, it's 1. Take different thing, their inner product is 0. Pairwise orthogonal. What does that mean? That and all these 1f, they live in where? This is a subset of F2 to the n, the vector binary string of length n vector space, right? So that means if they're pairwise orthogonal, the number of such sets is at most the dimension of the vector space F2 to the n. And the dimension of F2 to the n is n. So this implies the size of our family equals to the number of these pairwise orthogonal vectors, which is at most the dimension of F2 to the n is n. And that finishes the proof. And we know that this n can be realized by taking singletons. So it's quite a nice proof because it used very basic things in linear algebra and somehow build this surprising way of using linear algebra. The original problem is very combinatorial, right? And also shows this surprising difference between if you require even club size or odd club size, their behavior is very different. But if you look at this problem, you will see this problem, what type of problem is this odd town, even town? Again, you have some discrete structure. Last time in Mantel's theorem, you have discrete structure is a graph. And you consider discrete structure, the graphs with a common property P, say property P, and the common property P there is triangle freeness. They are all triangle free, they all have n vertices. And you care about some functionals defined on this discrete structure. And last case is the number of edges. And you want to maximize or minimize this over this family of discrete structure. So there, we try to maximize the number of edges over triangle-free n vertex graph. Here, you can put it in the same framework, right? It all look the same. You have discrete structures, now is subset of a ground set n. They all satisfy some common property. They all must be of odd size. And you also input a restriction that their intersection must be even. Now you ask, now the parameter you care about is the number of sets in this family. And you want to maximize that, right? It's always, you have some, in extremal combinatorics, you have some discrete objects. They have some common property. And you want to maximize or minimize some parameters about this family, okay? Any questions so far? So we've seen some combinatorial arguments for this that could be useful for Mantel's theorem, for this extremal graph theory problem. We've seen also linear algebraic methods that surprisingly also give us something non-trivial, some interesting combinatorial statements, this odd town, even town. Now let's give an example of using probability to prove something untrivial. This is the famous Ramsey type problem. Okay. Class is 210. Ramsey. So Ramsey theory, named after this person called Ramsey in the early 20th century. The philosophy, what's the philosophy of Ramsey? Philosophy. I think I spelled it wrong. This is I. Philosophy is that there's no complete disorder. Okay, no complete disorder. What does it mean? If you give me a huge structure, as chaotic as it may seem, I can always find some substructure that's completely ordered inside. And as long as your initial structure is large enough, I can get this ordered substructure can also be arbitrarily large. Okay, that's what I mean, no complete disorder. So we can find exist highly structured or ordered highly ordered substructure. Maybe say large in any sufficiently large system. Okay. So let me give you an example in terms of graphs. Let's do two edge coloring of complete graph. Let's consider two edge coloring of complete graph. So let's call this coloring. We have two. It's blue. We have two coloring. One is blue color, one is red color, say. Okay. So here's a coloring. And our goal is to find, you should think of this coloring as, it could be any chaotic coloring. It could be some arbitrary coloring. And all we want to find is to find a small subgraph that's a complete graph, such that all the edges you see in this subgraph, they are of the same color. They're all red or all blue. Okay, the goal is to find large monochromatic complete subgraph. Okay. Good. So to make this precise, let's give this definition of Ramsey number. RST. So ST is natural number. RST is the minimum. Oh. Okay, someone asked in the odd town, even town problem. Remember, if you require every club size is odd, the best we can do is n by our Alttown theorem. And we made a sharp contrast with when each club is of even size, we have 2 to the n over 2 many, right? So someone asked, is this optimal? Very good. So that should be the first question we should ask as we're trying to practice. So I will leave this as exercise for you to think about. Okay. Can you come up with a better one? If not, can you prove that this is the best we can do? Very good. So coming back to a Ramsey number, this is the minimum number, minimum natural number, minimum n, natural number n, such that no matter how we color, for any 2H coloring, of n vertex complete graph, we will always find there exists a monochromatic. That means all red or all blue. Monochromatic. No, sorry. I didn't write the symmetric version. So, RST, let me distinguish the color. So this is the minimum natural number n, such that for any 2 coloring, let's say blue and red coloring of edges of Kn, no matter which one you take, we can always find either blue Ks or a red Kt. A blue Ks just means S vertices, all the edges on these S vertices are blue. Okay, so this is the definition. Let's do warm up. Very easy warm up. Let me prove you R23 is 3. Okay, this is blue, this is red. So first of all, how do we prove lower bound? Lower bound for Ramsey number is by construction, right? You have to prove RST is bigger than something. That means you have to witness, you have an example witnessing that inside this example of 2 coloring, you cannot find the desired monochromatic structure. So your number must be bigger than that in order to force monochromatic structure. So lower bound is by construction. Okay. And upper bound is by argument. So let's do the lower bound. Lower bound, what do we need to prove? We need to prove R23 is strictly bigger than 2, right? This is very easy. If you have 2, what does it mean R23 is strictly bigger than 2? That means for 2 vertices, we need to find the coloring such that you cannot find the blue Ks or red K3, right? Well, if you color anything in blue, we are done. So we cannot color these 2 vertices in blue. You just color it red. This is an example showing that it's strictly bigger than 2. Okay, very simple. And upper bound, you need to show that R23 is at most 3 to prove equality. Well, for any 3 vertices, we know that we cannot color it blue, otherwise we get a blue edge already. So you must color it all red, then we get a red triangle, and we are done. Let's do a slightly non-trivial one. Do we have time? Yeah, let's do this one. R33 equal to 6. Let's first prove lower bound. Bigger than 5. What does it mean bigger than 5? We need to find the coloring showing that on 5 vertices, there's no red or blue triangle. Okay, this is what you can do. You can have a blue outside 5 cycle outside and have red 5 cycle inside. Neither color has a triangle and it has 5 vertices. By definition, this is a coloring that we cannot guarantee monochromatic structure. So R33 must be strictly bigger than 5. At most 5, at most 6. How do we prove it? Take an arbitrary vertex V. Look at its neighbor. You have 5 neighbors, right? You have 5 neighbors. 6 vertices, 5 neighbors, right? The edges incident to V are colored in 2 different colors. Either you are red or you are blue, right? But you have 5 edges, 2 different colors. By pigeonhole, some color appear at least 2 times. So pigeonhole at least 3 edges, same color. Let's say these 3 edges, right? Now what happened? We cannot have blue edges between any pair of these 3 vertices. Otherwise, you get blue triangle. So that means we must have red edges in between all of them, but that forces a red triangle. That's it. This is not what we want to prove today. We want to see the power of probabilistic methods. Let's prove something non-trivial. So I will prove, let's study most of the problems in extremal combinatorics. We would like to study the asymptotic, the growth of some function. In this case, the Ramsey function, RKK, as k goes to infinity, how does RKK as a function of k grows? RKK, we want to give a lower bound, meaning that we want to give lower bound on RKK. What does it mean? We need to find a 2-edge coloring of Kn for large n without red or blue, with no red or blue KK. That's what we need to do to prove lower bound. If we want to prove this is bigger than n, right? Good. This is also actually called, remember, we can model this, our WeChat network by graphs. Each user is a node. So if 2 are friends, you put an edge. Not friend, you put the non-edge there. You don't link them up. You can also view this as colorings. If 2 are friends, you put a red edge, right? If 2 are not friends, you put a blue edge. Very good. So how can we find a coloring with many, many vertices so that there's no blue clique or red clique, meaning there's no K people, they are pairwise friends, or K people, they are pairwise strangers on WeChat, right? So here's an example. We can at least do quadratic in K squared. We can do RKK is bigger than K minus 1 squared. This is very simple. What you can do is you can have different groups of people on WeChat, different community. Each group size is K minus 1. You make them all friends with each other. So this is a community, everyone is a friend of another. Here, everyone's a friend of another inside, everyone's a friend of another inside, everyone's a friend of another inside, same for all of them. And the number of groups is K minus 1, okay? So total number of vertices is what? k minus 1 square. That's the target bound. So how do we color it? Between different groups, they are strangers. Okay, let's say they're from different town. They're very far away. So you put blue edges in between. Very easy to check. There's no red clique of size k. There's no blue clique of size k, because for blue clique, you can take at most one vertex from each red blob. And there's only k minus 1 of them. The question is, can we do better? It's actually a major open problem, a major research direction to find explicit constructions. This is very explicit. I tell you exactly how the coloring looked like of a lower bound construction for diagonal Ramsey. Okay, so far nothing, no exponential bound in K is known, the lower bound explicit construction. But if you use probabilistic method, we can do much better than explicit construction. We're going to see now, to end this lecture, we're going to see an application of probabilistic methods to prove lower bounds on Ramsey number. Namely, we're going to give a construction of a two edge coloring of complete graph on n vertices, where n is exponential in K, much, much larger than K squared, without monochromatic KK. Okay. Now we're going to prove theorem. Let me start a new page. Now we will use probabilistic methods to prove lower bound on RKK. And this is an implicit construction, meaning that I just know there exists a coloring, but I don't know how it looked like. Implicit color construction. Okay. Theorem. This is due to Erdős. Early example of probabilistic methods is RKK bigger than n, where I can take n to be 1 plus little o 1, k over square root 2 times natural number e times 2 to the k over 2. This is just calculation. Don't worry about these numbers. Okay, I don't have much time left. Let me mention this big O, little o notation later. Just think of this as a constant, a fixed number. Forget about this. And this is a function of, this is a fixed number, right? Square root 2 is 1.414 fixed number. E, natural number, 2.78 fixed number. Just k could grow. We cared about this growth of function when k goes to infinity. But this is linear growth. What's important, we want to focus on this term. So forget about all these things. Just look at this term. We have an exponential in k growth, which is much, much better than this explicit construction we have on k, roughly k squared. We construct a much larger, a coloring on much larger complete graph without k vertex complete graph having all edges of the same color. Okay, how do we do that? The idea is very simple, but very smart, genius idea. Proof. So I let n to be this number, okay, for some n. Let's consider a random coloring, edge coloring of Kn. How do we do that? Let me give you an example. Here n equal 5, but imagine n is really large, n is this number. We're gonna color every edge randomly. So for this pair, I color it randomly. I flip a fair coin. If it's head, I color it blue. And for another one, I flip a different coin, independent of the previous one. And if it's tail, I color it red. So every edge gets a color with the same probability, red or blue. And it has nothing to do with other edges, independent of everyone. So it's an independent trial of coin flipping. Namely, for every edge, for every pair, every edge, ij in n choose 2. This is a notation for all pairs in N. Okay, you choose 2 elements from the ground set N. For all pairs ij, you color ij red with probability 1/2, blue with probability 1/2. Independent of all other edges. Good. What are we going to do now? What we don't want to see. We don't want to see monochromatic clique of size k. So let's estimate the expecting number of the bad configuration that we don't want to see. Okay? So let's estimate expecting number of red or blue cliques of order n. Number of monochromatic kk. Let's estimate this number. Linearity of expectation says that you just look at every k vertices and look at the probability that it's monochromatic there, you sum them up, right? You have n choose k, you focus on some k vertices here. How many choices of k vertices? N choose k of them. For every k vertices, you compute the expectation, the probability you see a monochromatic clique there. You add them up by linearity expectation. That's exactly the expecting number of monochromatic kk, right? So times the probability that a fixed k set is monochromatic. Okay, but what is this probability? Well, each edge gets color red or blue with probability 1/2. So what's the probability that all edges, they all be red? One edge is 1/2. All red means all k choose 2 edges must be red, right? And that's the probability that all of it is red times 2. Because it could be all blue, which is the same probability. Yeah. So far, it's very easy. I didn't do anything magic. I just randomly color it, and I compute the expecting number of monochromatic clique. Compute the expecting number of bad configurations. The magic is the very last step. If this expectation is less than 1, this is the interesting part. This expectation is less than 1. And by our choice of this parameter, 2 to the k over 2, if you plug in here, do the computation, this is less than 1. I will leave it for you to verify this inequality. So this is true. I skip the calculation. What does it mean, expectation less than 1? That means sometimes it's bigger than 1, sometimes it's smaller than 1. But this expecting number of monochromatic clique is an integer from 0, 1, 2, 3, 4. There's no 0.5 monochromatic clique, right? So that means sometimes it's 0, sometimes it's 1 or 2. It must be sometimes 0. Otherwise, the expectation will be at least 1. So we prove implicitly, indirectly, that there exists an outcome of the random coloring with no bad configuration that we would like to see. That means there is a coloring that's good for us. Okay. So this implies that there exists a good coloring. So I will not write the definition of good. That means there's no red or blue clique. And this finishes the proof. Does it make sense? Any questions? So that concludes. Actually, I go a little bit over time. That's it for today's class. So to summarize, we see 3 different types of statements. The first statement is subgraph, discrete structure is graphs. We study Mantel's theorem, the subgraph containment problem. We use these pure combinatorial proofs, inductions, and some other combinatorial proof here using maximum degree. And then we reviewed a different discrete structure sets, and then use somewhat surprisingly linear algebra to prove some interesting combinatorial statements. And at the end, we have yet see a different type of methods using probability that could give us a very, very good lower bound on this Ramsey number. Okay. Any questions?
Or maybe the first page at the top of the
Or here, here, more. Oh, 4 here.
No, actually this. Yeah. Does it mean that we could find at the top? Does it mean that we could find all trees on T indices? Or just one?
Actually, here you can find all trees. Yeah. This sometimes they call universality results. In this case, you can find all trees. It's a very simple greedy embedding. You can try it. Yeah. Good. Other questions? So next course will be on Thursday, the same time. We're going to resume then. We will cover one more basic example, so Ramsey theory on sequence of numbers, the early sequence, also another very famous one. And then we're going to move on to more systematic study on different topics. We'll start with continuation of Mantel's theorem in extremal graph theory. Okay, thank you for listening today. See you guys on Thursday.